One of the challenges for the next generation of particle accelerators is to generate very, very short bunches of charged particles, so things in the femtosecond scale, sort of 10, 100 femtoseconds. This is the sort of time scale where it takes light about 100 femtoseconds to cross the width of your hair. The end application for many of these accelerators are looking at the fundamentals of how chemistry, biology, materials actually behave, where the science of these things are actually happening on the femtosecond scale. Where the particle accelerators come in is they allow you to actually examine the dynamics of these materials.
Free electron laser is a very intense source of light. Unlike a conventional laser, you can generate gigawatts of power, and you can also generate light in any frequency you like.
You have high energy relativistic electron bunches which are made to wiggle through a periodic magnetic structure, and when they wiggle they emit some radiation. In a free electron laser it goes one step further, where the radiation interacts back onto the electron bunch and causes the bunch itself to form tiny little microstructures, which then makes the radiation or the emission of the X-rays or the light even stronger.
CLARA stands for the Compact Linear Accelerator for Research Applications. It's essentially a free electron laser test facility. So we're utilizing the machine to demonstrate very new and unique applications of free electron lasers.
There are many concepts that are actually shown in simulation and computing that look like they'll be able to work, but actually demonstrating them in a proof of principle machine is essential before you go to building a many £100 million facility. CLARA is a facility specifically aimed at actually demonstrating some of these concepts, as well as lots of advanced research on the conventional accelerator. Novel accelerators are trying a completely different approach.
If you compare laser accelerators to RF accelerators and you look at the wavelengths, the wavelength of a laser is hundreds of nanometers, as opposed to RF, which is tens of centimeters. And this means that if you're wanting to accelerate a bunch of electrons, you're looking at much smaller wavelengths.
So in the Latte lab, see here, we're using lasers to generate these very, very high frequency fields to do the femtosecond control of charged particles.
Terahertz and laser accelerators have a use in the fact that they are smaller than standard RF accelerators. So if you're saying a medical accelerator, you're wanting to shrink down your costs, so you might want a smaller building. So if you can shrink down your accelerator, that reduces your costs, which is better for everybody. The biggest technical challenge with laser and terahertz accelerators is the fact that they are so much smaller. One of the problems is if you go to lasers, for example, you're looking at hundreds of nanometers. So suddenly you're trying to fit a millimeter bunch into a 100 nanometer structure.
So a laser plasma accelerator uses a very high intensity short pulse laser and you produce a plasma. A plasma is the fourth state of matter. And when you take all the sunlight that falls upon the UK and you focus it down to the width of a hair, you can produce the very high intensity conditions that are required to accelerate these electrons. So the high intensity laser pushes the electrons away, producing a cavity bubble. And these very high electric fields then subsequently accelerate these electrons to very high energies close to the speed of light. Laser plasma accelerators are truly the next stage for accelerators. They are very compact and they can accelerate to very high energies. So the next step is to really try and make laser plasma accelerators more reliable and improve the uniformity of these beams, and also trying to make them increase the repetition rate so they can be applicable to a wider range of industrial application and also in medicine as well.
I think the most exciting part is that we're doing very new things. I think that the challenges that we're being faced with haven't fundamentally been solved to the extent that are needed for the projects that we need to deliver. And so being given the responsibility to come up with appropriate solutions, provide capabilities that very few groups have internationally, and then being able to deliver on large-scale projects is a real benefit and attraction for the work that we do here at the lab.